Pressure is simply defined as this. It's the amount of force over a given area. And so if I were to say to take my hand and were to put a force of say 5 newtons, Newton being the metric or SI unit of force, put a force of 5 newtons against a wall, then it would have a force of 5 newtons. The pressure, though, would depend on what surface I'm pushing into the wall. If my hand is on, say, a book pushing into the wall, then that force is spread out, and so I have a lower pressure. If, on the other hand, my hand is forcing a pin into the wall, then that force is all focused onto a very, very small answer, or very, very small area. And so by having a small area, I'm going to have a very large pressure. And so sort of taking a look in general is that if we have our general one, as we say here, that pressure is equal to force over area, then what we know is this, is when the force goes up, if the area stays the same, then the pressure is going to go up. And of course, in sort of reverse of that is if we, let's say we're going to leave the force the same, but instead what we're going to do is we're going to make the area go up. If the area goes up, then sort of because it's inverted here, by having a larger area, we're dividing by a larger number, the pressure is then going to go down. And so overall, this is basically sort of what we start off with when we're talking about pressure. This is our definition. Now, for measuring pressure, unit-wise, because we're talking about force over area, a common US unit of pressure, in this case, is basically the pound per square inch. You'll see this like when you're doing tires. They'll call PSI is what they call pounds per square inch, or we could express it sort of like we have right here, sort of pounds per square inch. Right there. And so if you'll excuse me just a moment, because I have pulled out my cable. Let's see here. There we are. So as we can sort of say, as we see right here, we have pounds per square inch right here. We could also, as we said, call that just PSI, pounds per square inch that way. And so those are two different ways of expressing sort of our setup here. That's sort of the common, the U.S. customary system. In the metric or SI system, then we're going to measure force, as we said, in newtons. And so for the most part, you said 4 newtons is roughly equivalent to 1 pound. And so therefore, a newton is about a quarter of a pound, a little over 4 ounces. A little over 4 ounces there. And so we'll measure area, though, in meters squared. And so whenever we basically set this up, we'd say that our force is going to be in newtons, our area is going to be in meters squared. And we'll talk about what that is in a little bit here. So if we want to define the pressure on a 230 square meter roof with a snow of weight 2,100 newtons, then we're basically going to set it up like this. We say the pressure is equal to the force. The force here is 21,000 newtons. And that's going to be divided by our area here, which is 230 meters squared. And so at this point, all you have to do is take out your calculator. And so if you get those out, you then do the math. And when you do this at 21,000 divided by 230, and you get a pressure of 91.3 newtons per meter squared. And so setting this up, we get 91.3. And the units are newtons per meter squared. And so that's basically how you would calculate pressure. So let's take a look at sort of continue what we have here. Take a little more look at pressure. The unit of pressure. So the SI, the metric unit of pressure, is called the Pascal, named after a guy by the name of Blaise Pascal, who's a mathematician, scientist, and otherwise great at everything type of guy, sort of Renaissance man. And a Pascal is basically defined thus, that 1 Pascal is equal to 1 Newton divided by 1 meter squared. Those are the units that we used before. And so if we talk about, say, so this type of unit, there's one slight problem with the Pascal. And the problem with the Pascal is that Pascal is an incredibly tiny unit. If you think about a meter squared, you're talking about something that is, over 3 feet by over 3 feet in a square that's that size, a 3 foot by 3 foot square. So even slightly bigger than that. And then you're going to take something, you're going to spread 4 ounces over that. And so it's like you take 4 ounces of peanut butter and spread it over something that's an area that's basically 3 1/4 feet by 3 1/4 feet. The pressure caused by that's going to be tiny. Just a really tiny pressure here. So we're going to want to use a better unit here. And we'll talk about that in just a second. Before we get there, we need to talk a little bit about atmospheric pressure, because when we're talking about gases, which we're going to be doing in this unit, the really important one here are pressures from gases. Now, atmospheric pressure is basically the force, the pressure caused by the atmosphere. It is caused by the impacts of the atoms and the molecules in the gas or in the atmosphere against a surface. You can think of it like this. In any gas, the molecules are moving pretty quickly. They're running around, occasionally they run into each other, but if there's a surface, a container, then the molecules of that gas, of the atmosphere, are going to run into that container surface. When they hit the container surface, they strike it, they're going to impart a force. And so when you talk about air pressure is simply caused, or atmospheric pressure is simply caused by the force of the gas atoms and molecules impacts on the surface. And so those impacts are what cause the pressure here. If you think about it, that means there's basically two different ways that you could manage to increase air pressure. One is to increase the number of impacts. You can do that by, actually there are three ways to increase air pressure. One is, well, just simply to decrease the area. If you make a smaller area, you're going to have a higher pressure. The second one is going to be that you can increase the number of impacts by putting more gas atoms in. If you want to increase the pressure in your tires, this is how you do it. You add more gas to it. You add air to your tires. When you add air to your tires, there are more atoms. Therefore, there'll be more atoms that'll be hitting, running into the surface, and so therefore you're going to have more pressure. A second way you can do it is you can speed up the impacts. You can make it so that the atoms that hit are going to hit at a faster speed. You do this simply by speeding the atoms up. To speed the atoms up, you heat up the gas. If you heat up a gas, you're going to have a higher pressure, and we'll discuss that a little bit later here. So back to sort of talking about what atmospheric pressure is. If you were actually to measure what atmospheric pressure is in pascals, what you find is that 1 atmosphere, and 1 atmosphere is defined to be the pressure at sea level at 0 degrees Celsius. And so that's sort of our definition of 1 atmosphere right here. If you measure this in pascals, it's 101,300. This is a huge number. It's also a little unwieldy to use. And so since it's a little unwieldy to use, we're instead going to want to convert this into something else. And so instead of using pascals, we're instead going to use kilopascals. The abbreviation here is kPa. This should actually be a lowercase k right there. But so it's kPa. So kilopascals, 1,000 pascals. If you convert it here, then instead of 101,300 pascals, we can write that 1 atmosphere is equal to 101.3 kPa. Now, down at the bottom here, if you notice, I've got sort of a quick sort of cheat sheet guide that you're going to want to keep up with. This is basically everything that's equal to atmospheric pressure. We're going to see a number of different units for pressure here. And keeping up with this and writing this on one of your colored sheets, if you've got it, is basically going to let you, give you a way to convert between your units. And so this is a little bit important as we go through here. So this is sort of what we have so far for units of pressure. So we've got that 1 atmosphere is 101.3 kilopascals. So continuing as we go on, another common unit of pressure is called the millimeter of mercury. And so it's abbreviated. The abbreviation here is simply mmHg, millimeters of mercury. And we're going to define things in such a way so that 1 atmosphere is 760 millimeters of mercury. Okay? We'll talk about why we use such a weird unit a little bit later here, but that's for right now, it's all we know. 1 atmosphere is 760 millimeters of mercury. Now, because of the fact that millimeters of mercury is a little bit of an odd sort of unit here, it sounds sort of strange here. Another way of expressing this unit is to call it that a millimeter of mercury is called 1 torr. Torr is short for Torricelli. It's one of the scientists who started working with pressure, and so we also can call it 1 torr. And so then, if we have that, so atmospheric pressure down at the very bottom here, atmospheric pressure 1 atmosphere is equal to 760 millimeters of mercury, and thus is also equal to 760 torr, because torr and millimeters of mercury are the same thing. So this millimeters of mercury, odd sounding name for a pressure. Millimeters is a length. Mercury is an element. How could a length and an element give you a pressure? And the answer to this comes back to sort of a very central question. How do we measure pressure? How do we know what pressure something is? And so let's take a little bit of a look at that. To measure pressure, measure relative pressure, the pressure between two different things. If we have one gas that has one pressure and another gas that has another pressure, we'll use something called a manometer. And so we talk about a manometer here. And so this device right over here on your right side of the screen is basically a manometer. What it has is it is a U-shaped tube, usually of glass, and it has two ends. One which is connected to one gas. We're going to call that one basically P1 right over here. And another one which is connected to another gas. We'll call that P2. Oftentimes what happens is that one of them is connected to like a container of gas. In this case, P2's the one that's connected to a container. That's the reason why it has this little sort of spout coming off of it. And the other side is connected just to the open atmosphere. That's why this one's over here. Now, what you then do is well, actually even before you connect to the gases, but you will connect to the gases. Before you do that, you're going to add something else. Is that inside the tube, you're going to put some fluid. Usually they use mercury. And so we'll sort of assume that we've got some fluid down in here. And so we have some little fluid that fills up this container just like that. Now, for this fluid here, if the pressure for P2 and the pressure for P1 are the same, they will both push on the fluid equally, and so the fluid levels will be equal. So sort of like I've drawn right here, is that the level of fluid is exactly the same on both sides. And so for this right here, P2 is going to be equal to P1. And so I know the pressures have to be the same on both sides. But what if that's not true? What if instead that we have something a little bit different here? Let's say that instead of the fluid levels being equal, that what we find is this. We have P2, we have P1, and we set it up, we find out that we have fluid levels here and here. Looking at this right now, the way we sort of got this set up is that the level that's on the P2 side is higher than the level on P1. So if the P2 level is basically higher than the P1 level, that means that we know that, that P1 is pushing very, very hard, while P2 is not pushing very hard. It's a very, very small pressure that we have on P2. So if that's true, then we know that P1 is going to be greater than P2. We can say that about the pressures. Now, the exact opposite can also be true. And so let's say that we've got a situation where instead of the sides being like they were right there, is that we find that you put two more gases in here, and you find that the levels are like this. And so if that's the case, then we can see that P2 is pushing down very hard, P1's not pushing down very hard, and so we know that the pressure P2 is bigger than the pressure P1. Okay? And so the difference in the fluid levels is going to basically tell us what the difference in the pressures is. Now, it just tells us right now which one's greater. How do we know exactly how much different the pressures are? Well, this comes to the issue of why we call this millimeters of mercury. Remember that we said that inside this container, we basically have mercury. So there's mercury down in here. That's the fluid that we have here. If we were to take this, and we were to stretch this out, and we were to measure the height difference between each section, that height right there, if you measure that in millimeters and your fluid is mercury, then you are going to get a difference that's going to be in what they call millimeters of mercury. So let's say that right now that we find that we get a total of 12 millimeters is the difference in our two heights. If that's the case, then because P2 is greater than P1, then I know that P2 has a pressure which is 12 millimeters of mercury higher than P1. To make this a little more concrete, let's say that we've got this at atmospheric pressure. We know we're at atmospheric pressure, which is 760 millimeters of mercury. So we're 760 millimeters of mercury is the pressure P1. We know that of these two, P2 is greater than P1 because the level is lower on P2 than it is on P1. And so we'd say, how much lower is it? It's 12 millimeters lower. The pressure is, the pressure on P2 is 12 millimeters higher than the pressure on P1. Since the pressure on P1 is 760 plus 12 gives us a total pressure of 772 millimeters of mercury, or torr, also will work. And that's how you figure out the difference in two pressures. So this is basically how you go about using a manometer to figure out what the pressure difference is between two fluids, between two gases. So this right here works pretty well. The only problem that you run into is that using a manometer only works if you already know one of the two pressures. So we had to know, as we sort of did on this last one, is that we knew that the pressure P1 was 760 millimeters of mercury. It's at atmospheric pressure. But what if we just wanted to measure what atmospheric pressure is? I want to know what the pressure is that's in my room right now. In order to do that, I'd have to have something to compare it with. And if you're going to compare something, usually the best way to compare something is to find basically where it's zero and then compare it to that. For example, what if I were to take this guy right here and I'm going to set up my manometer, and instead of setting it up sort of the way I have right here, is that I'm going to go ahead and I'm going to make it so that P1 is equal to 0. If P1 is equal to 0, then I know that P2 simply has to be equal to 12 millimeters of mercury, because P2 is 12 millimeters higher than P1. The 12 millimeters, it's lower than P1, and the difference is 12 millimeters. And so that would be one way of setting this up. To do this, where you create one side basically a vacuum, you make the pressure 0, we're going to need a different device. And this different device is not called a manometer, but it's called a barometer. And so let's take a look at the barometer. So if I want to measure absolute pressure, the pressure at any one point, I want to basically set it up so that one side of the manometer could have a pressure of 0, the total vacuum like I said before, and this is a barometer. So over on your right, you can sort of see a picture of this. What we have on our barometer is that we have a glass tube. The glass tube basically stretches down and sits in a pool of mercury. Up in the top glass part of the manometer, the pressure is 0. No pressure at all out here. On the outside, there is air pressure that's going to push down on this mercury that sits in the pool. That air pressure will force the column of mercury to go up, and so I'll have sort of a level that'll sit somewhere right up here. And so this is basically how I have right now sort of set up my barometer. Now, for your barometer right here, here's basically the way that this sort of works, is that if I were to take this out at atmospheric pressure, once again, we said this is sea level, 0 degrees Celsius, then if I measured the height from the bottom up to the top right here, I would get 760 millimeters. This is the reason why 1 atmosphere is defined as being 760 millimeters of mercury, because that's the height of a column of mercury in a barometer at atmospheric pressure. And so this is sort of where this comes from here. So this is basically a manometer versus a barometer. Barometers are used for measuring absolute pressure. Manometers are used for measuring differences in pressure. And that being said, let's take a look at something else here. Let's take a look a little bit at vapor pressure. So let's suppose that I have like a little plate full of water. So I just have a liquid. Let's say it's at 20 degrees Celsius. Now, any liquid that's at a certain temperature has molecules that have many different kinetic energies, but they average to be that temperature. So a temperature is basically an average of kinetic energies, in the same way if you have a class of people, that if you were to look at the height of that class, you have two options. You can either add up everyone's height and find the total height of the whole class. This is sort of what heat is, the total kinetic energy in a substance. Or, on the other hand, you could average them. And averaging their heights would basically give you an average height, which is very similar to temperature. Temperature is an average kinetic energy. But like any average, there are some, so if I have it 20 degrees, that's my temperature, so that's my average kinetic energy. What that means is I'm going to have some molecules that are going to be cooler than 20 degrees, and I've got some molecules that will be warmer than 20 degrees. Of those ones that are warmer, some of those warmer ones are moving fast enough that they can manage to escape the liquid and turn into a vapor. And so this process, where molecules turn into a vapor even though you're below the boiling point, is called evaporation, sort of common sense there. Now, we also know by common sense, if you want something to evaporate, all you have to do is heat it up. The higher the temperature of the liquid, the more molecules you're going to have, which are going to be fast enough to be able to escape that liquid and turn into a vapor. And so these molecules then escape, turn into a vapor, and are now out in the atmosphere. Now, if your water was in a closed container, those vapor molecules, they escape into the atmosphere, into the sort of the gas region above your water in your water bottle, is that they'll go into the water bottle here. They're up in sort of the gas region up there at the top. They're floating around up there. But since they're moving quickly, they're going to run to the walls. When they run to the walls, they're going to impact the walls. They're going to create a force. That's going to put a pressure on the walls. And so the escaped water vapor molecules, they're going to exert a pressure on the walls, and this is called the vapor pressure. So this is our vapor pressure right here. You have a colored sheet, which is a vapor pressure chart for water that tells you at various temperatures what the vapor pressure is. Now, the vapor pressure for water chart tells you both the vapor pressure in millimeters of mercury and in kPa. Those are both the same value. So looking at it 20 degrees, you can see that the vapor pressure of water is 17.5 millimeters of mercury, or 2.33 kilopascals. Since as you heat it up, you're going to get more molecules that will turn to vapor, that means there'll be more molecules that will be hitting the sides of the container. That means you're going to get a higher vapor pressure. So going up from 20 degrees to 60 degrees, we see at 20 degrees the vapor pressure was 17.5. At 60 it's 149.4. So we get a much, much higher vapor pressure. Simply because you heat them up, you're going to have more molecules floating around. They're vapor molecules. They're going to hit the surface more, and so you're going to get higher pressure from those. And so this is basically how you set that up. Now, as we talked about before, the atmosphere is going to exert a pressure against any surface that it contacts with. In this case here, that's due to the impact of the gas molecules onto any surface that it's going to impact with. So in this case right here is if we have this liquid surface that's sitting here that is basically giving off these gases, these vapor molecules, is the atmosphere is going to exert a pressure on that. If it's at atmospheric pressure, that's going to be 760 millimeters of mercury. And so that atmospheric pressure that exerts back onto the liquid sort of pushes back against these molecules that are trying to escape. That is, they push back against the vapor pressure. Now, if you take a look at your vapor pressure chart, then you'll see that, as we said, the temperature increases, we're going to see the vapor pressure increase. At, say, 60 degrees, the vapor pressure is 149.4 millimeters of mercury, but atmospheric pressure is 760. Atmospheric pressure, therefore, in a sense, is sort of winning against that in that fight, which means that only a few molecules are going to be able to escape. Now, if you look on your vapor pressure chart, you'll see that there is a point where the vapor pressure actually equals 760. That is, the vapor pressure starts to win that battle. That temperature is 100 degrees Celsius. 100 degrees Celsius, boiling point of water. The definition that we have of the boiling point is that the boiling point of water is the point at which the vapor pressure and the atmospheric pressure are equal. Because at that point, then the vapor is able to escape. It doesn't just, not just some of the vapor molecules are able to escape, but all of the liquid water molecules are able to turn into a vapor because that force that's pushing back against them is basically overcome by the additional vapor pressure that you have that's existing. So if we had atmospheric pressure at 760 torr, 760 millimeters of mercury, then we know water will boil at 100 degrees C because we said the vapor pressure of water is 760 torr. That's on your vapor pressure chart. Now, if you think about this, there are two ways then to boil water. One of which is to raise the temperature of the water so that the vapor pressure of the water increases. If the vapor pressure gets to the point where that vapor pressure is equal to atmospheric pressure, then we know that basically it'll boil. This is sort of like this. I have atmospheric pressure that's right here. I have my vapor pressure that's right here. As that temperature goes up, the vapor pressure rises until the point where they're right on equal. When they're equal, I've got boiling. On the other hand, there's a second way that I could manage to boil something. I have my vapor pressure right here. I have my atmospheric pressure right here. Instead of raising the vapor pressure by increasing the temperature, I could lower the atmospheric pressure. And if I lower the atmospheric pressure enough, I can manage to get the atmospheric pressure to equal the vapor pressure. And so when that happens, it will also boil, but it boils at a cool temperature. This is the reason why, if you think about, you've seen high altitude directions on cooking instructions. At higher altitudes, the air pressure is lower. If the air pressure is lower, then water will boil at a lower temperature. If it boils at a lower temperature, and you've got to cook things longer to manage to get them the same amount of cooking because they're cooking at a lower temperature. And so this is an example of how vapor pressure and boiling point are related. And so we will get on a little more and some more details about this and about gases on our next lesson, but this finishes up what we've got here for now.